eta r, and finally what when it will strike to the it's going to describe spiral path. Not exact shape. I'm able to draw it, some rough diagram. It should be curved one. I'm able to make it a perfect curve. Yeah. Okay, now this was the initial point. It started. Okay, let's get into the somewhere here. Let's try to write all the possible the forces that are acting. Then it'll be easy for us to analyze what actually going on. How the viscous drag, what is the property of viscous drag? It should directly act opposite to velocity. So how the velocity here will be directed? The diagram. Yeah. No, first I'll get into the velocity vector. There's a velocity vector. And the angle between them is theta, where theta will be less than 90. There's a strict condition because of viscous drag. And how the viscous drag should act opposite to this velocity vector. I'll move the diagram. Please, all of you do make observation because the forces how we take that matters a lot. Alpha v square. How the gravitational force will act. So here I'll resolve this velocity. One component of velocity will be v cos theta. The other component will be perpendicular, v sin theta. 90 degrees I'm putting. So you should be very careful. V and R will not be perpendicular because of this spiral path. And how the force due to gravity should act. No. Okay, fine. So these are the things here. No, let me resolve this. Components, let me resolve. Alpha v square cos theta Fine. So just make observations. So these are the forces that are acting alpha v square. Somebody please mute it. What is this? Alpha v square. This is a viscous drag. This is a velocity where v will not be perpendicular to r, where r is the radius vector. Already I indicated, no? Theta less than 90. So this what basically happens here. And finally, what will happen? It will revolve and this one. So let's try to write equation. Let's try to write the equation along radial direction. Along radial direction, m v cos theta, derivative of this should be equal to gm mass of planet. Yeah. Mass of moon, no, it is. I will take it here. It's mass of satellite BMS into r square minus alpha v square cos square theta. Component of viscous drag will be there. This is one equation. Then along tangential direction, v sine theta continuously, the speed of that will be varying. Even the theta also will be varying. So we do get, we cannot solve. Huh? We cannot solve. Okay, let's see that is asking something. Determine how long the satellite will stay in orbit until it falls to the moon's surface. Okay, this what generally if a student thinks, no, actually should think this much only. We have to put a condition. If the viscous drag is so high that what happens, it may just complete 1 or 2 rotations and it will fall onto the moon, the satellite. But even the cosmic dust will be very small, will be of very small order. Because of that, what happens, it's going to go several rounds. Then finally what will happen, will enter. In that case, we will become perpendicular to r. This is actually the general thing. So when you have to take a condition like this, when the viscous drag is high, usually viscous drag will be very low. For very low, you should not think in this way. So this is actually the basic thing what in IDO, the question was asked, keeping this in, means a student should analyze like this, then you should come to a prior condition. Okay, when this situation will occur, when the viscous drag is very low, when very high, okay, this condition occurs. So usually the viscous drag or the cosmic dust, what is acting no, will be very low. In that case, it's going to go several rounds. V will be perpendicular to R. I had to, as a teacher, I think I should analyze both the cases. That's why I'm just showing it this one. So this is for high viscous drag. For low viscous drag, we'll see that one. For low viscous drag, V will be definitely perpendicular to R. The problem will become very simple. It's going to go spiral. Diagram not exact. Okay, let's, yeah. So this is R, and there's a basic property that occurs. Sir, how do I come to know? I think better before they have proposed here, low viscous drag, high viscous drag. The conditions will be like this. Okay, now all provide required centripetal force, the gravitational attractive force. So here strictly and the viscous drag will act in this direction. So there'll be tangential retardation as well as this one. So let me directly start with Fe should be equal to Gm ms r square. Please do make observation of the things here. So this will provide and the orbital speed v square by r gms by r square. Expression for orbital speed will be this. Already we know this. I think keep it here now. What is the total energy of the satellite? Should be equal to, shall I directly write? It should be equal to minus, directly I'm writing it. This should be the total energy of satellite. Both potential as well as kinetic energy is included. Now what will happen to this energy? This energy will continuously will decrease. So I'll differentiate this. dE is equal to minus Gm ms by 2r square into dr.
Plus, sir.
No, plus only, I made plus. A few small things. What will happen to kinetic energy of satellite? Increases or decreases? Anybody? Because before entering any calculations, first we should have a background. What will happen to the speed of the satellite as it approaches the surface? Here somewhere I'll give the thing. V1, V2. V1 should be greater than V2 or V1 should be less than V2. You know concept, huh? You should apply. That's what I feel. V1 should be greater than V2. Sir, how do you can say, what is the expression for kinetic energy of satellite? Just simple idea. So what will happen to radius r? R decreases. If r decreases, kinetic energy should increase. Objective questions, be careful. So, but viscous drag is there as the decrease in potential energy will be such that it is able to overcome the viscous drag, and also there will be increase in kinetic energy. But sir, viscous drag is doing negative work. Yes, I do agree. Viscous drag does negative work. The decrease in potential energy is equal to increase in kinetic energy plus work done to overcome viscous drag. That's what happens here. Sir, how do you can say? I'm not here just bluffing here. I'm clearly telling that one. What is the expression for kinetic energy of a satellite? I'll write K, simple. That's what we know. And if R decreases, we know spiral path, radius decreases, kinetic energy should increase. Now, what will happen to angular momentum? Angular momentum is given by mvr. And what is the expression for mass of satellite? ms gm. Look at now, angular momentum also will increase, no? Sorry, R decreases, angular momentum decreases. So R decreases. It'll decrease. Okay, let's get into the calculation part. Our question is only to calculate that time. Tell me like from where I should bring the time parameter into the picture. The viscous drag does work. The viscous drag does work. So shall we go for that one? The decrease in potential energy. Oh, so okay, the work done by viscous drag dE is equal to F into ds. What is F? F should be equal to, here I'll introduce the rate at which mechanical energy decreases. That should be equal to F into ds by dt. What is ds by dt? there should be the power F into V. Okay, dE by dt. So dE is equal to, further I'll write it as F V into dt. What is F? F is alpha V square V dt, or this will become minus alpha V cube dt. Keep it in hand. Now, what is dE is equal to? I need one more. I'll get into calculation part. Okay, dE should be equal to GMMS dr by 2r square equal to minus alpha V cube into dt. Okay, let's solve this. What is the expression for V? Orbital speed GMMS 2r square dt minus alpha. This should be equal to GMR to the power of 3 by 2. Fine. This is orbital speed. But sir, it's a spiral speed. At any distance, radial distance r, the speed of the satellite is given by this particular thing. Okay, rest all everything will be G capital M. Yeah. I think now only the limit, suitable limit is what we have to solve. M gets eliminated, mass of the satellite, ms 2 r square here, r to power of 3 by 2. Anybody, how much will get? R will be? Anybody, what should be the power of R?
1 by 2.
1 by 2, okay, fine, yeah. This will be root R, we'll take it. Now the limits will be ms 2 r to the power of minus 1 by 2 dr. This should be equal to alpha root gm into dt. What should be the limit I should go for? Initial distance is eta r, and the final how much will be r. Finally, it strikes the surface of the earth. I'll write the answer. You later on check it. Our question was asked with a low viscosity. Cosmic dust means it will be low viscous only. Rather than, I think, the present exam objectives that KL varying, that they are very